A new system can reorient over 2000 different objects with a robotic hand facing both upwards and downwards. At just 1 year old, a baby is more dexterous than a robot. Sure, machines can do more than just pick up and put down objects, but we are not quite there as far as replicating a natural pull toward exploratory or sophisticated dexterous manipulation goes. Artificial intelligence firm OpenAI gave it a try with Dactyl, using their humanoid robot hand to solve a Rubik's Cube with software that is a step toward more general AI and a step away from the common single task mentality. DeepMind created RGB stacking, a vision-based system that challenges a robot to learn how to grab items and stack them. Scientists from MIT's Computer Science and Artificial Intelligence Laboratory CSAIL, in the ever-present quest to get machines to replicate human abilities, created a framework that is more scaled up, a system that can reorient over 2000 different objects with a robotic hand facing both upwards and downwards. This ability to manipulate anything from a cup to a tuna can to a Cheez-It box could help the hand quickly pick and place objects in specific ways and locations, and even generalize to unseen objects. This deft handiwork, which is usually limited to single tasks and upright positions, could be an asset in speeding up logistics and manufacturing, helping with common demands such as packing objects into slots for kitting or dexterously manipulating a wider range of tools. The team used a simulated anthropomorphic hand with 24 degrees of freedom and showed evidence that the system could be transferred to a real robotic system in the future. This type of in-hand object reorientation has been a challenging problem in robotics due to the large number of motors to be controlled and the frequent change in contact state between the fingers and the objects. And with over 2000 objects, the model had a lot to learn. The problem becomes even more tricky when the hand is facing downwards. Not only does the robot need to manipulate the object but also circumvent gravity so it doesn't fall down. The team found that a simple approach could solve complex problems. They used a model-free reinforcement learning algorithm with deep learning and something called a teacher-student training method. For this to work, the teacher network is trained on information about the object and robot that is easily available in simulation but not in the real world, such as the location of fingertips or object velocity. To ensure that the robots can work outside of the simulation, the knowledge of the teacher is distilled into observations that can be occurred in the real world, such as depth images captured by cameras, object pose, and the robot's joint positions. They also used a gravity curriculum where the robot first learns the skill in a zero gravity environment and then slowly adapts the controller to the normal gravity condition, which, when taking things at this pace, really improved the overall performance. While seemingly counterintuitive, a single controller, known as brain of the robot, could reorient a large number of objects it had never seen before and with no knowledge of shape. Many small circular-shaped objects like apples, tennis balls, marbles had close to 100% success rates when reoriented with the hand facing up and down, with the lowest success rates, unsurprisingly, for more complex objects like a spoon, a screwdriver, or scissors being closer to 30%. Beyond bringing the system out into the wild, since success rates varied with object shape, in the future the team notes that training the model based on object shapes could improve performance.